everyone, welcome back to another video. I hope you're all doing well. In this video, we're going to be taking a look at a question regarding HNMR and how to use the data booklet to give the correct answer for questions as such. Now, really, when it comes to do with IR Spectrum, really all you need to do is look at the data booklet. It's actually very, very simple. The IR spectrum is nothing to worry about. It's a very simple topic. The HNMR spectrum, I made a video on it about 2 days ago, and I'm going to cover some more questions on HNMR. And hopefully by the end of the video, you guys are more comfortable with this topic. And I have been getting a few requests to cover this from subscribers. So this question is from May 2019, time zone 2. And the question starts off with this, where we have a chemical reaction of ethyl, which reacts with steam to form this substance over here. And then they have said that there are two possible products of this substance, where it can either be A or it can be B. And based on that, they have given us some information on the IR spectrum of this product. It is one of these two, right? They've given us some information on of the IR spectrum of the product, and they've given us some information on the HNMR spectrum of the product. Now, really, I kind of discussed this in my previous video. HNMR and IR spectrum and mass spectrometry, these are all methods which you can use to determine the structure of a mystery compound that you have formed, right? And this is pretty useful to chemists, and it has a lot of practical uses. In fact, even at university, actually my last sort of chapter in my chemistry course was to do with HNMR and spectroscopic methods. We learned about them in quite a bit of detail. So if you are planning to take chemistry in university, you are definitely going to come across this topic, and it's pretty important. It's really fun. And I hope that you learned something today. All right, so let's take a look at the question. So the first part is deduce whether the product A or B, using evidence from the spectra together with sections 26 and 27 of the data booklet. Okay, so whether is it A or B? We have two options. We have A. So A, we can see we have an alcohol, right? We have an alcohol over here, COH, that's an alcohol group. And we have this double bond over here, right? This alkene double bond over here. And then for B, we have this aldehyde group, this carbonyl group over here. Sorry, not aldehyde. So this aldehyde would be this whole thing, and carbonyl would be just this over here. This would be the carbonyl. Okay. So the first thing you do, typically when questions like this come up, is you look at the IR spectrum. Because what does the IR spectrum tell us? IR is infrared, and what does this tell us? This basically tells us, in very simple terms, what type of bonds there are in the compound that we are looking at, in this mystery compound, what type of bonds are present. And each type of bond gives a different, or it gives a specific, it gives transmittance at a specific wave number, right? So each type of bond has a different transmittance at different wave numbers. So if we suppose look at this IR spectrum over here, what we're looking at is strong sort of peaks. So strong peaks like this. So like this particular peak should stand out to all of you. This peak right over here, it's nice, it's strong, it's clear, and it's touching this point over here. That means a pretty strong peak. So we should be looking at that. That's one. And two, we should also be looking at peaks that are not present. And now you may be confused. What do you mean by peaks that are not present? So what I mean by that is, if you look at, for example, compound A and compound B. Now, in compound A and B, what is the main difference between both of them? One, that compound A does not have this present in it, this carbonyl group. And two, that compound B does not have this OH bond present, and compound B also does not have the C double bond present. So for each of these bonds, so for the C double bond and for the OH, you expect to see something on the IR spectrum, right? And if you look at your data booklet, if you flip over to section 26, you see that C double bond C, the alkenes, the wave number at which we are supposed to see a peak at is between 1620 and 1680. Now, 1620 and 1680 is somewhere over here, right? And are we seeing medium, weak, multiple bands? Well, not really. We're not. We're seeing this irregular sort of stuff. This is not what we're looking for. This does not really fit this does not fit the characteristic of alkenes. So that is one hint. But you may still be a bit confused after this. So really the second thing you can look for confirmation that A is not your molecule is you can look at the OH kind of peak. Is an OH peak present? Now, if you look at your data booklet again, if you see for OH, you have a peak at 3,200, between 3,200, and you have it between 3,200 and 3,600. Do we see anything? 3,200 to 3,600 is over here. And the peak is supposed to be strong and broad. Do we see anything of that sort over here? No, we do not. We see a small peak over here. We see a small peak over here. That does not signify anything. So that clearly indicates to us that this mystery compound does not have an OH present. It does not have a C double bond C present because the peaks are just not there. So we can automatically eliminate option A. So A is not going to be a product, right? So you can, in the identity of the product, you can state that is, A is not our product. Rather, it's going to be B. Okay. Now, they've asked you to state one piece of evidence from the infrared spectrum. Well, I told you, you can either look at what's there. You can look at this broad peak over here, this broad peak. What does this broad peak signify? I totally forgot to explain this. I'm so sorry. This broad peak signifies the presence of a C double bond O. This is what this signifies. And if you look at your data booklet, if you look at infrared data, you see that aldehydes, ketones, carboxylic acids, and esters, where this C double bond O is present, the wave number for that is between 1,700 and 1,750, which is perfectly where we want it to be. That is exactly between 1,700 and between 1,700 and 1,750. So it's perfect. So these are basically two confirmations that we have from the infrared spectrum. One, that C double bond O is present, and two, that C double bond C and O single bonded H, this alcohol group, both of them are not present. So we can use these three pieces of information to determine that B is in fact our correct answer. So when they ask you to state one piece of evidence from the infrared spectrum, you can say any one of these three pieces of evidence that we have. But what I would always prefer you to say is what is present. So I would prefer you to say that a strong, broad peak at between 1,700 and 1,750 is present, which signifies the presence of C double bond O in the compound. So if I was to summarize that, I would just say strong peak between 1,700 and 1,750, indicating the presence of C double bond O. Now, this is really a shorter answer. In the exam, I would encourage you to slightly word this better. I've just kind of gone and I've done it the short way. Okay. So next part of this question. It says, one piece of evidence that it is compound B from the HNMR spectrum. All right, okay. So in addition to the IR spectrum, they've also given us the HNMR spectrum. Now, again, if you've watched my previous video, what did I tell you guys about the HNMR spectrum? Why do we use the spectrum? Well, we use the HNMR spectrum to determine the number of hydrogen environments which are present in a molecule. So over here in this HNMR spectrum, we can see that there are two peaks. These two peaks over here, this one and this one, these two peaks indicate that there are two hydrogen environments present, right? That is what these two peaks indicate. There are two hydrogen environments present. Now, out of these two molecules, between A and B, let me just draw out A and B, right? So it looks something like this. And then we have, oops, nope. And then we have B, right? So these are our two molecules. We know based off of the HNMR spectrum that this mystery compound has two hydrogen environments as indicated by these peaks. Let's count the number of hydrogen environments in each one of these molecules. Let's just do that. So we have this H over here. This H is attached to an oxygen. It's by itself. It's in its own hydrogen environment. We can name that hydrogen environment number A. This hydrogen over here, this is very different to A because this hydrogen over here is not attached to an oxygen. So this is in a different hydrogen environment. So we can name this hydrogen environment number B. These two hydrogens are both in the same environment, right? Because they're attached to the same carbon and they're in the same environment. And this environment that these two hydrogens are in is very different to this environment. And why is that? Well, simply because this hydrogen is attached to a carbon, which is then attached to an oxygen. However, these hydrogens are attached to a carbon, and this carbon is then attached to another carbon and nothing else, right? So that is like the difference between these two environments, and they are clearly different from one another. So this is another environment by itself. This is another environment by itself. So that is environment number C. And as you can see, there are three different hydrogen environments in molecule number A. So if you look at molecule number B, of course, you have this one hydrogen over here, which is in its own environment. And then you have these three hydrogens, which are all in the same environment. And you could call that environment number B. And this molecule over here, molecule number B, has two hydrogen environments. And that makes perfect sense because we see two peaks in our HNMR spectrum. So one piece of evidence from HNMR, well, you can simply state that molecule number A has three hydrogen environments and molecule number B has two hydrogen environments. And we see this in the HNMR spectrum where we have peaks at two different points indicating two different hydrogen environments as opposed to three. So hopefully you get that. Let me just write that down. So one piece of evidence from HNMR is two hydrogen environments molecule A has three. So again, this is a very shortened, condensed answer. I would definitely encourage you to word this better in the exam, but hopefully you get the idea of what I have done. Okay, just erase all of this. Okay, so over here in part 5, they've asked us, deduce the splitting pattern that you would expect for the signals in a high resolution HNMR spectrum. Okay, so this is something that I did not cover in HNMR in my previous video. What does this mean? What does this mean when they say the splitting pattern? Well, they have said that when you have a high resolution HNMR spectrum, so right now we have this low resolution HNMR spectrum, right? It just shows you one peak, two peaks, right? Two peaks over here. If you have a high resolution HNMR spectrum, it would look something like this. You would have, of course, your scale over here, and then you would have the peaks, but these peaks are these some of these peaks may be split up into smaller peaks. So if you have this peak, it would have sort of three smaller peaks kind of clustered around it. And then this peak over here might have just these two peaks clustered around it, right? So in a high resolution HNMR spectrum, this is something that you can expect. And why does this happen? Why do we see the splitting? Well, the splitting occurs when one hydrogen environment is close to another hydrogen environment. So, example, if you have, let me just take up molecule B. Let me just erase all of this and let me just take up molecule B. You have molecule B, which looks something like this. Oops. Double bond O, H, 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 H. Now, these hydrogen environments, so this hydrogen environment and this hydrogen environment, A and B, these are neighbors, right? These two environments, they're neighbors to each other. Now, how do you determine if a hydrogen environment is a neighbor to another hydrogen environment? Well, it's actually quite simple. Take a look at this. Pick any hydrogen from the first environment. So, okay, if I have environment number B, I will pick hydrogen, I'll pick this hydrogen over here, and then count the number of bonds, that the second hydrogen is away from you. Or sorry, the hydrogen in the other environment is away from you. Count the number of bonds between the hydrogen in one environment and the other environment. So basically, this hydrogen over here, it has 1, 2, 3 bonds between itself and the hydrogen in the other environment. That means that they are neighbors. So basically, if the hydrogen from one environment is 3 bonds away from the hydrogen in the other environment, they are neighbors. Okay? Anything more than 3 bonds, you cannot consider them to be neighbors. However, in this case, we can see that all 3 of these hydrogens, so 1, 2, and 3, they're all neighbors to this hydrogen over here, and vice versa. All these 3 hydrogens are also neighbors to this one hydrogen. So what happens is when these two environments are close together, right? When they're close together, on the HNMR spectrum, we see something called splitting. The splitting pattern, as I showed you, are these small lines that occur as a cluster, right, around one peak. So these splitting patterns indicate the number of neighbors that are present for a hydrogen in a particular environment. So, for example, if I was to see the um, if I was to see a HNMR spectrum, right, I want to find out how many neighbors does a particular hydrogen have. So if I have a hydrogen in this environment over here, suppose at 3, and I have a hydrogen at this environment over here at 7, I want to find out how many neighbors each of these hydrogens have. So then we look at the splitting pattern. Now, if, for example, you see a splitting pattern which looks something like this, where we can see it's split up into 4 different peaks, that would mean that that hydrogen has 3 neighbors. If you see a splitting pattern as such, where it has 2, that means that that hydrogen has 1 neighbor. If you see a splitting pattern like this, where you have 3 different peaks, that means that that hydrogen has 2 neighbors. So you can probably see where I'm going with this. The splitting pattern is n, where n being the number of hydrogens which are neighbors, plus 1. That is your splitting pattern. So let's take a look at this again. Let me just take a look. Let me just erase these circles over here. Let's just take a look at this. Okay? Let's take a look at what the splitting pattern would be for this hydrogen over here. The splitting pattern for this hydrogen over here, well, the first thing you need to do in order to determine the splitting pattern is to look at the number of neighbors that a hydrogen has. So let's take a look at the number of neighbors for this hydrogen over here. Well, it has one neighbor, two neighbor, and three neighbors. And remember, before you determine, or how to determine if they're neighbors, is check the number of bonds that are between the hydrogen in one environment and the hydrogen which is supposed to be its neighbor. So how many bonds are between this hydrogen over here and this hydrogen? Well, there are 1, 2, and 3. What about this and this? Well, there's 1, 2, and 3. And then again, for this one, we already saw it's 1, 2, and 3. So we have determined that this hydrogen over here has three neighbors, being this, this, and this. They're its neighbors. So what would the splitting pattern be? Well, I told you the splitting pattern is n being the number of hydrogens which are neighbors plus 1. That is the splitting pattern. So the splitting pattern would be 4. And you can't just write 4. The word for this that we use to describe this 4 is quartet. So the splitting pattern is a quartet. And that would be over here, quartet. Now you may be wondering, why did I write this quartet at 9.8 ppm instead of 2.83 ppm? Sorry, 2.3 ppm. That's because this in the HNMR spectrum, the chemical shift is much higher for hydrogens which are close to an oxygen. So this hydrogen is very close to this oxygen, and thus it has a very high chemical shift. So the chemical shift for hydrogens which are attached or close to oxygens have a very high chemical shift. And this hydrogen is pretty close to this oxygen. It's just a bond. It's just 2 bonds away. It's pretty close, and that's why it has such a high chemical shift. That's just some extra information. Okay. So we've determined that the chemical shift for this is at 9.8, and it has 3 neighbors. So its splitting pattern, it's going to be a quartet. It's going to have 3, and it is a quartet because remember our formula for determining splitting. It's n being the number of hydrogens plus 1. Now, what about for the other 3 hydrogens over here, which are at 2.3 ppm? 1, 2, 3. Remember, I want you to remember something. When determining the splitting pattern, you do not consider other hydrogens which are in the same environment as you as neighbors. So for instance, I would not consider this hydrogen and this hydrogen to be a neighbor for this hydrogen over here. That does not work. We only consider neighbors, or we only consider hydrogens which are not in the same environment as you to be neighbors. And you can think of it like this. Do you consider people living in your own home as neighbors? Well, no, they are not your neighbors. They're your family, right? That's in kind of the same way. You do not consider hydrogens which are in the same environment as you as neighbors. You only consider those hydrogens which are in a different environment to you as neighbors. So in this case, these 3 hydrogens, these 3 hydrogens are all brothers over here, or sisters, right? These 3 hydrogens only have one neighbor, which is this guy right over here. And remember, what did I tell you about the splitting pattern? The splitting pattern is determined by the number of hydrogens which are neighbors to you plus 1. So it's going to be double, right? Double. You're going to have a double split, or 2. And the technical term for this double is called a doublet. For if it was, for example, imagine if it was 3, it would be a triplet. A 4 is quartet, right? I don't think we have gone above that in IB, to be honest. But yeah, you need to do a doublet, quartet. They also have singlets. If you have no neighbors, it's a singlet. If you have 2 neighbors, it's a triplet. If you have 1 neighbor, it's a doublet. If you have 3 neighbors, it's a quartet. Okay. Hopefully you guys have understood that, and hopefully I have managed to drive away any apprehensions you had with this topic. Again, it is difficult. It is a difficult concept to grasp, Please let me know if you have any other questions. I'll be more than happy to help you. Send me your questions on Instagram or send it to me via email, and I'll try to make a video on it, or I'll explain it to you. And that's it for this video. Thank you so much for watching. Take care of yourselves, and I will see you in another video with another question. Goodbye.